Well, hello everyone. Welcome to part 12 of my DLL injection into all processes. And today we will again continue coding Windows driver, and we'll be coding the shellcode, or continue finishing it up for DLL injection. So without wasting any more time, let's load up our IDE, and we're using Visual Studio 2019, and open up our inject all solution. If you remember, we left off on our DLL ASM64 assembly file, which was doing base-independent injection of a DLL into the process. But if you also remember, if we switch to x86, that we also created a 32-bit I apologize, a 32-bit file, which we did not create. I apologize, so let's create it now. So let's do new item. We'll use the header file, because it doesn't matter at this point. And let's just call DLL ASM32, and extension is ASM. Now this is important. Let's hit add, and all we need is an empty file. So let's copy this part, because it's actually going to be reused. We'll adjust it. Okay, the comment up above basically tells you what the function will be doing. It's a special way we're writing a shellcode to basically execute this function. And by the way, let's change it here, because that's the declaration for it. And basically this function will be called as a user mode APC during our injection, and it will be called from the APC that we queue from the kernel, but it will run in the user mode, and that will do the actual DLL injection for us. And as the input parameter, we will specify base address in the normal context of this module. We will need it later to unmap it from the target process. And in the system argument 1, we will have a DLL name of the DLL that we will be injecting. In this case, the DLL name will be a known DLL, which will be mapped section into that process and into the system. So we basically don't need a path. All we need is just a name. And okay, because we are in x86, we have to follow certain rules. And this one is just, really don't have to think about it. It's just kind of like a default convention here. Okay, now alignment is 4 bytes. And because our function is a standard call, we have to follow also name mangling, which is we have to start it with underscore and end with the number of bytes that are passed, and which is 3 parameters times 4, which is 12. And let's specify here how exactly those parameters are passed. And they're passed on the stack. And just copy this so I can actually use it for all of them. Okay, the first parameter is at offset 4, 8, and 0C. And that's what is being passed. Now, if you want to see how exactly the shellcode works, this is the link for the blog post, and you can just go to this URL and just look for how to implement getProcAddrForMod in shellcode, and that will, clue you in. So let's finish this file. Let's skip it down this way and put end p, and then we need end at the end. And we will write several modules here. Now, if you several functions. If you remember what we did here, we had our function that did the actual work, and then we also had a helper function at the bottom that was resolving proc address from the module. So we need to adjust it here. And we need to specify how those input parameters are being passed. Now, this function is, obviously very similar to what we coded above, except, it will be just different, different bitness. Okay, so this one is ESP plus 4, and this one is ESP plus 8, which is, again, both parameters are passed on the stack, and we don't need any name mangling here. So this will be kind of a quick prototype of this function, and now let's write it. So again, I kind of explained most of it. So first we need save non-volatile registers. Again, when I wrote a 64-bit implementation, I kind of explained all of this stuff, well, partially, but here we'll just be pretty much doing the same, except it's a different bitness. So right now I'm just saving non-volatile registers that we have to save across, inside the function. And then we need to reserve some space for local variables, because again, we'll be using them. And let's see, I calculated that I will need 14 hex amount of space. And basically, since we created all those pop, commands or instructions at the end, let's do the opposite. And we need to restore stack and non-volatile registers. And again, we just do it in reverse. So we have to add 14H to ESP, or the stack pointer, and then we do pop EBX, kind of like, again, go in reverse order. Then we pop EDI, just have to align it right. Then we pop ESI and pop EBP. Now, if you ask me why are you doing, these registers, why not just 2 of them? Well, I kind of know that I'll be using them in the code, but basically you can look at the calling convention for Microsoft for, std call for x86, and it will give you a list of registers that you need to save basically across the function. And they are really simple. It's EBX, EBP, EDI, ESI, and let's see, an EDI. Right, so EBX, EBP, EDI, ESI, ESP. So that's what we need to do. And okay, so we got the prologue and epilogue here, which is nice. And at this point, we just need to do the same PE manipulations as we did in our x64. So we need to do this calculation here. Again, I'll be just adjusting this code for the bitness. So instead of RBX, I'll be using EBX, and we're taking it from ECX. Okay, you know what? This procedure will be actually, I need to write it down. Let's do it as fast call. So in that case, we don't have to deal with the passing it on the stack, because it's kind of like annoying to calculate all the offsets and stuff. And with the fast call, I can just simplify things. So let me review real quick. So yeah, absolutely. If we do fast calls, so this one would be ECX, and this one would be EDX. And then, yeah, we don't have to deal with the stack, which is nice. So in this case, ECX would be the base address right here. So we'll save it in EBX like we did before. And then over here, we need to calculate length of our function name, which was passed in EDX. And let's see, so what we do here is that we pass it into EDI, and then we set EAL to 0, so we're going to be looking for 0, and ECX must be -1, and then we repeat, and then we load EDI into EDX, and then we then we subtract EDX from EDI, and EDI is the end where we found 0, and then we subtract EDX from it, and EDX is the beginning of the function. So at the end, EDI or EBP would contain the length of the function name in chars. Okay, so let's put some space here. Now the next thing, we need to walk the PE header. And again, see what I'm doing, I'm just kind of like copy and pasting it, because again, it will be pretty much similar stuff. And in this case, we're using EAX and EBX. Now the offset is still the same, because it's, you know, the DOS header here. Okay, now then we have EBX plus EAX, and offset is a little bit different. It's 7/8, and I'm just taking it from a cheat sheet. Basically, obviously, I'm not memorizing it. Okay, so EAX plus EBX, in this case, EAX would be image export directory, pointer to it. And then we need to calculate the number of offsets. In this case, we can't use R9 because we don't have that register. So let's use ECX, which would be EAX plus 18. And let's write it here that ECX is the actual number of names, or B, and B it's just kind of like a pseudonym. Here let's check that it's not 0. And if it is 0, we need to go to our bad, and bad would be at the very end. And what we will do here, we just say XOR EAX, EAX. And let's put a comment here that just says that nothing was found. Kind of like, you know, bad result. And so, okay, that's our bad clause. So let's go back. And let's see, so we need to get pointers to PE structures. But before we do that, because we can't really use ECX, because, you know, we don't have enough registers. You see, like R60, you know, the X64 had all these registers, like 10, 11, 12. Here we don't have them, so we have to store our you know, our intermediary values in the stack. So let's just use ESP+4 to store ECX, and we're just gonna say so that not ECX but ESP+4, that's where we'll store our number of names, or B. And then when we do XOR ECX, ECX, and move it into ESP, in this case, ESP, let's see, originally 0 or A. Okay, so it's kind of like a local variable that we will set up. Okay, so in this case, we need to get our PE header structures. So here it's a little bit different. We have to do a little bit more work, because again, we can't use these fancy 64-bit registers. So, but that's okay. So we'll just reuse ECX as our scratch register. So we are going to read this into ECX. Then we're gonna add E0 bx to it, basically this stuff, which we will not be doing. And ebx, if you look back, it's basically the image or base address, right? So, and then what we do, we put it into a temporary location. So, and in this case, ESP plus 10 would be address of functions, okay? Then we will again reuse ECX, and here, by the way, it's EAX. Oops, so we are doing EAX plus 20 and add ECX EBX, and here we will put ECX into ESP plus C, and ESP plus C would be address of names, and again C, it's obviously hex number. Okay, and let's do the last thing. So ECX would be EAX plus 24, and then we do the same thing here. Kind of tells you how many more instructions you need when you don't have enough registers, like in this case, in case of x86. Okay, and here it's plus 8, and let's make a note here that ASP plus 8, the local variable, is address of name ordinals. Okay, so let's save it. Okay, so we did this right here. So we set up this parameter right here. And what we need to do now, we need to begin our loop. So just copy and paste. Actually, you know what? Let's go like so. Okay, so I'm going to add a little bit of spacing here so we can actually read it better. Okay, so we pretty much do the same thing here. We use binary search because all of our names are alphabetically sorted, which is nice. And so here, instead of doing this fancy kind of like Lee instruction, we have to do a little bit more primitive computation, but that's still fine. So now ESP, if you remember, is our A. Right, so then we need to add our B, which is ESP plus 4. Okay, that's our B. And then we need to divide by 1, which is the same thing. Then we need, again, a little bit different instruction here. Let's see, we do ECX, ESP plus C. Okay, get to see what I'm typing. Okay, ESP plus C is address of names, right? And then move EDI, ECX plus EAX times 4, which is this thing here. And then we add EDI to EBX, and EBX is our base address, if you remember. Okay, and then we do ECX equals to EBX, and ECX would be name length, because remember EBP is the function length, name length in chars, so that's what we need. And let's highlight EBX, because again EBX is our base, DLL base. Okay, and then we have ESI equals to EDX, and EDX is a function name. Let's make sure that that's it. And it comes from the function itself, from the entry parameter. Okay. And at this point we do again the same compare, the same search. And we skip, we go out if we didn't find anything. And if we did find a match, we actually celebrate right here, and we do these, these computations. So in this case, let's use let's say our scratch register, which is ECX, and we need to get address of names, which is ESP plus 8, and that is right here. I'm sorry, address of ordinals, which is ESP plus 8, and then we need to move pretty much the same thing, except there is ECX right here, and EAX would be right there. Okay, next line. Okay, we need to again use our scratch register, which is ESP plus 10. And again, if you look at ESP plus 10, let's see, where is it? This is our address of functions right here. Right, that's what we need. And we do it right here. Again, instead of reusing like we were able to use the register, we actually have to read it into scratch register first in this case, and then read from it, but pretty much the same thing. Okay, so no change here, and eventually we just need to add EBX to our EAX, and EAX will contain the address of the function, and then we go out. Let's see, and the out would be right here. So we have to restore our stack and all the registers in it. So that would be it. Okay, and then if we didn't find anything, we jump here. And let's see, what do we have here? Let's just copy all this stuff because that will be very similar. And it goes right here, right before the bad clause. And let's kind of quickly go over it. So we jump here, and then depending on the result, we can jump JS to here, which is 3. Okay, now we need to in this case, we need to add 1 to ordinal. So we can do increment EAX, and then we just move, because again, it's a local variable. We just move it into it, so we don't need this. And then jump to 4, and 4 is the check. And 3 is just setting our B, and B is plus 4, and we put EAX into it. And here we need to compare, but before we compare, we need to read our value, one of them, into local register, and then we can say compare EAX to ESP plus 4. And here basically what we're doing is that A is ESP and B is ESP plus 4. And the way we can tell is by going here. So here is B and ESP is A. All I'm doing, I'm just converting the 64-bit code into 32-bit. Okay, so, and then we get bad, which is nothing found, which is we set EAX to 0 and return it. Okay, well, let's try to build it. Oh, by the way, need to change something. We obviously don't need to build a 64-bit version here. And let's switch to release and do the same thing, because obviously it's not going to work. Okay, so let's try again. And let's see, fake, rebuild. Okay, and syntax error. Let's see, what does it not like it here? Oh, obviously, it's a move instruction. In 64-bit, we had to use let's see, where is it? Move signed. It's because we were moving D word into 64-bit word. Yeah, into 64-bit register. In here, we just move D word into EAX, which is 32-bit register, so there's no problem here. And let's try to build it again. And it builds, which is nice. Let's do release, and I think in release, let's see if it builds here. I doubt it will, because it needs yeah, it needs safe structured exception handling. So, and what we do, we go into our DLL ASM32, and it's in general, no, I'm sorry, it's in advanced. We need to say use safe exception handling, and it should build now. Okay, nice. So let's switch back to debug. Okay, so at this point, we have our getProcAddrForMod module, which we can use. Okay, so let's get back to our main UserModeNormalRoutine, and let's write its code. Now, we have to do a little bit of a prep work here. So we set the input parameters, and they will be passed on the stack. So as always, we need to save non-volatile registers, and I always want to put pos instead of push. I'm not sure why. So we don't need too many of them. Okay, and then we need to reserve space for local variables. In local variables, it's basically when you declare, when you go into a function and declare something like this, this is a local variable. So it's really easy to do in C, but here we actually have to know how much space we need and reserve it. So, and the way you do it is kind of like backwards by decrementing number of bytes from ESP register. Okay, and since we did this kind of thing, we'll have to restore them. Let's just put it at the very back. Let's just say restore stack and non-volatile registers. The reason I want to do it right away is because you can see here what you've done. It's pretty easy. You can just reverse it. ESP plus 10 hex, and then we did pop EDI and pop EBP, because again, you just kind of reverse the order. And if you don't see it, all you have is this. You have to scroll back and forth and actually see what was there. So that's why I like to do it, ahead of time. Okay, so at this point, we have all that figured out, and let's look back into our 64-bit assembly, and we need to do just basically copy and paste here as well and adjust it for the 32-bit code. Okay, so we need to get base DLL for NT-DLL. Now here it's a little bit different. Again, we take EAX, and the segment register is FS, and the offset is 30. And by the way, since we are using this FS, what we need to do, if we go all the way up, and we need to use one directive here, we need that, put the assume thing. What this does, for some reason, compiler, when it sees the use of one of the segment registers, it starts complaining. It's a very legacy thing, but it goes back in the day when they were using them for actual, to specify actual segments in memory. So right now, it's really not used for that. So Microsoft uses it internally to store references to on all the internal structures. But still, I guess for legacy reasons, the compiler will complain if you don't use this assume FS, not FS, colon nothing. So let me just put a little comment here. So needed to use FS segment register in the code below. Okay, so it just kind of tells what this is for. Okay, so we have offset 30. Then we read EAX from offset, a little bit different. offset C, and at LDR. By the way, let me just quickly correct these things, and that will be E. Okay, so at C will be LDR, and EAX at offset 1C will be, yeah, it will be double linked list, and then we get ECX at offset EAX plus 8. That will be DLL base, and then we store it in EBP, and we can do that because we just saved it here. And EBP will be our DLL base, which is nice. Okay, so that would be it. And then let's see, what else did we do? Well, we get pointer to loader load DLL, so let's do that. So let's see, how would we do that? Well, unfortunately, the way we resolve the name here is by using a relative offset in this LEA instruction. Well, in x32, in x86, I'm sorry, in 32-bit, we don't really have this option, so we can't resolve addresses like this, like relative basically addressing. They added it later because it was very convenient, but in x86 it did not exist. So what we need to do, we need to get a pointer to our string somehow else. And let me show you one technique that has been used since long days of x86, and that's by using call instructions. So let's just kind of do, I don't know, like right between them. I'm gonna add some space so it will be easy to find them. And let's just say get string, and for that it's a proc and it's a private one. And let's put end proc, and again I'm going to put some spacing so we can navigate easily. And I need to align it by 4 bytes. And what it will return, address of string, which will be ASCII string with 0 at the end. And the string that it will return is this. Okay, so now the way we do this is just we make a call instruction to, let's say, something as such. Then we do pop EAX and return. Now this looks very strange. So why would you just call like here and then just pop EAX and return? Seems like some broken assembly. Well, it is not. If we, let me just copy it from here. If we put this little line here, so basically what it does, when the execution comes to this line, it calls here, and pop returns the address where we're supposed to return. Well, the address we're supposed to return is the address of this string, and that's what we need. So we literally get the address of the string in memory, which is kind of like not the best option here because we put our data right in our code. But for shellcode, this is absolutely fine. What we need to do though is we need to make sure that this address is aligned on a 2-byte boundary. This is kind of like important for the Unicode string that we'll be using later, but for now we need to make sure that. So string must be aligned on a 2-byte boundary. And the way we do this is that we need to add a little bit of a spacing here. Now this call instruction will have an uneven number of of bytes. So by adding nop, which is no operation, doesn't do anything, we simply push it down. So this part will be aligned on the 2-byte boundary. Okay, so and that's what our little function here does. Very simple. It's kind of like an old trick in the books by using call and by using this kind of thing right after it. And it will totally confuse this assembler because it will try to interpret this as instructions, as CPU instructions, and it will look really funny, but at least it would work. So, okay, well, at this point, since we have our function to resolve loader load DLL string, let's go back and we can actually call it to get, let's just write it, get pointer to loader load DLL string, and it will come as EAX, and then we can put it into EDX. If you remember, EDX contains the function name of a function that we want to resolve. Oops, sorry. And all we need to put, let's see, what do we need to put? We need to put base address into ECX. Well, the ECX already contains the base address, as you can see here, so we don't need to do anything else. So at this point, this function will resolve our load or load DLL, and we need to check it in in EAX. And if we fail, we go to 2. In this case, it will be 2. And let's put it like, I don't know, right here. Okay, so at this point, if you remember, let's see, where were we? Let's go back. Okay, so in this case, we saved our RAX in R10. In this case, we don't have those fancy registers, but we can save it on the stack as a local variable. Oops. Keep putting that X in there, thinking I'm in C, but I'm not. Okay, so we can do that. And again, this is just saving our address of our loader load DLL. And then just kind of let's do the same thing as we did here. So we need to get length of our DLL name. And now in here we have a little bit of an issue. So let me just first change everything that I can see. So ECX would be 0, EAX is already EAX, decrement ECX, and EDX and EDI. Okay, and then we do repeat, scan string word, and subtract EDI from EDX, and EDI would be the length of DLL name. So all we need to do is set up EDI. Now, if you remember, let's look back here. Now, our EDI was the DLL name, right, that we saved over here. Now, if we look back, and the DLL name, well, did we even save it? Well, we didn't need to save it because it is actually on the stack as ESP+8. So let's take it here. But we need to actually adjust it. Let me just put a comment here that EDI is injected. So let me make sure I spell it right. Injected DLL name. Well, the problem is that stack pointer has changed since we got it here. So this is kind of tricky part. Let's see what changed it. First of all, we added 2 pushes. So let's just add. So it was ESP+8, and then we did 10. Let's see. Hold on. So 8 plus, I'm sorry, so it's not 8, so we get 4 and 4, that will be 8. So let's just do plus 8. And then we subtracted 10, so we need to add 10. So now this kind of an ugly contraption would be actually referring to this, which is injected DLL name. I know it's kind of confusing, but basically what happens, like this offset was true when we just got into this function, but then we started, you know, changing ESP by basically pushing it back. We changed it by 4, then by 4 here, and we changed it by 10H here. And that's what I'm doing basically. So originally it was this, then we did twice by 4, so which is 8, and 10 is that subtraction. So right now it's this. So we can actually calculate the name, I mean not the name, the length of the DLL name. And let's see what else. I'm already lost here. Okay, so we're here, and at this point we need to get this part, which is the calculation of our Unicode string, right? Now right off the bat, now these offsets would be the same, but this one would be not, because again there's no need to align it by 8 bytes, and here it's aligned by 4 because we're in 32-bit. And let's set this up here. Now it will not be stored this far away because we don't have shadow stack. We can just store it just immediately on the ESP. So and in this case we just basically do 2 offset di, then we subtract 2 and offset 0 would be length. Yeah, I'm just kind of going here 2 0, and this one is offset 4, and we are putting EDX, and let's make sure that we have something in the EDX, and we do. This is let's see, what do we have in EDX? EDX is actually EDI, and EDI is injected DLL name. So basically we are putting the injected DLL name into our buffer, which is a pointer. So that is nice. And then we need to actually call our function that we just resolved. So let me just copy and paste. Okay, now load DLL. Now first, the call doesn't come from R10. Instead, it comes as a dword pointer from the ECX. Now let's see, where did we save it? Well, we saved it over here. I'm sorry, not ECX, from ESP plus C. But there's a little but here, because, you know, we will have to pass all these parameters, because, you know, we can't pass them as fast call. So we need to actually check. If we go and look up the function again, the calling convention is NT-API, and NT-API is basically a standard call. So that's what that is. So we have to pass all of these things on the stack. So, well, let's prepare it. Let's say EAX would be 0. And you know what? We'll have to do it separately here. So let's just kind of like do it this way. So push EAX. That would be, again, what we're doing. I'm starting from the top here, and that's basically 0. Then we do the same thing, and we say that flags is 0, right? And then we need to push module file name, and let's say we need to put an address of ESP, and address ESP is our module file name, which is our Unicode string. And again, we pass an address, and local effective address will basically put address of this into this. Okay, and then we need to load an ECX, an address where to put our module handle. Technically, we don't need it. Okay, and here we need to push EDX, and right before we need to push ECX. Now this is a little bit different because again, we're not doing fast call here. Okay, so let's just review it. So push EAX, which is 0, we push 0, then we push another 0 for flags, then EDX is our module name, which is ESP, address of ESP, and that is right here, which is the address of our Unicode string, which is correct, and then ESP plus 8, and this is basically following right next Unicode string. That would be ECX, and ECX is the path to file, is the module handle. We don't really need it, it's kind of like a dummy parameter here. So okay, that's very nice, and now we need to see, how far do we need to offset our ESP, because again, we saved our return address in ESP plus C, but then we changed ESP, and namely we changed it here. We did 4 pushes, so what we can do is that we can say 4 times 4, and that will account for these 4 pushes. So this line will actually call our loader load DLL. Again, as always, we can't really do anything here with the, if it fails, so we just skip it. And further on, we need to, let's see, what else do we need to do? Oh, we need to call our getProcAddress to get NT unmapped view of section, the name of it. Okay, so we have this function right here, but what we don't have is the name, so we can't resolve it as such. So we need to modify our little function here to actually resolve it. And let's say that we are taking it from here, and I'm just gonna modify this whole thing. Make sure that I didn't make any mistakes here. So get pointer to string, address of this, 2-byte boundary. Pretty much everything is the same. Aligned by 4. That's the name that we're looking for. And here you go. So very simple. And again, we need to call it right here. Now let's see. Let's just say what we're doing here. Let's say get pointer to this name over here, and it will come in EAX. So what we need to do at this point, we need to move it into EDX. Oops. Because again, if you remember, EDX has to be the name of the function, and we can tell it by looking here. And ECX has to be the base address of NTDLL. And we take it from EBP, which is indeed base address. and then we call to resolve NT on map view of section using this function that we made earlier. And let's see, at this point we need to prepare to return, so let's restore our stack and non-volatile registers, because again the result is in EAX. So we can do that, and then we can check the result of getting the function pointer, and in this case we test EAX, which hasn't been changed, and if it's 0 we go to fail like we did before. And in here we just need to do this kind of thing. Oops, keep clicking things in the wrong place. And you know what, we can do fail also. And let's see if we copy and paste, and let's see what we have here. So again we have important notice here. Okay, well, let's look at a fail clause, which will be pretty much the same, except we need to pop all of our registers. Now, if you remember, now let me just put a comment here. If you remember, our function is actually standard call, and standard call basically says that we have to get the parameters out of the stack. So that's why we need to pop them, which is 4 times 3. That is 12. Need to pop own arguments because of standard call. So this is important. Don't just do ret, otherwise, you know, your function will fail. And in this case, we need to remember to add. Let's see, we need to find preprocessor definitions, and we need to add for debug configuration to make sure that this int debugging break is included. Okay, so that will be our fail, but now we need to actually do our jump, and the jump is a little bit more tricky. Now, jump is obviously into EAX, but we need to set the parameters correctly. So if you look, let me just put like a comment and put before. So what we have before is that ESP contain return address from this function. Then let me just copy it from here. And let's see. Okay, ESP plus 4 contains base address of this module plus 8 injected DLL name, and this one is unused. So the way this has to work, let me put after, for our API is that we have to pop this address off the stack, and just copy it this way and just show you what I mean. So we need to pop off this one. Oh man, I just can't type today at all. Right? And then if we do, this becomes plus 0, this becomes plus 4, and this becomes plus 8. Now, why are we doing this? Well, we basically need to get rid of this return address and put it over here. Because basically, if you look at the stack that we will send into this function, and by the way, let's look up its calling convention. it's also NT API, which means that this is standard call, right? So this means that these two, it will have two parameters, and the third parameter would be its return address. Okay, so, and that's how we need to set it up, and then it will basically pop off all those parameters and return to where it's supposed to go. So let's kind of do this real quick. So if we take, I don't know, like EDX, like our scratch register, ESP plus 4, right? So basically what we need to do, we need to put return address over here, and over here we just don't need anything. We just need like this -1 thing, right? So but first we need to read our base address of the module. So we did it into EDX. Then we need to pop this ESP, in other words, move it here. It used to be here, but now we move it here. Okay. Then we need to move or put our return address right here, like I showed. Okay. And then we need to do move word dword pointer ESP plus 4, and let's see, 1 2 3 4 1 2 3 4. It's just my way of setting basically -1, and that would be process handle right here. And this is, remember, like that macro get current process, which is basically -1, and then move ESP plus 8, we put EDX, and EDX is our base address. Okay, so, and let's do it right here, that this is base address. So again, kind of like we just had to like reshuffle stuff on the stack. Again, we put return address here, then we put process handle over here, which is basically -1, and then we put our base address over here. And at this point we can actually call EAX, which we resolved from over here, which is the address of NT unmapped view of section, and that will provide our needed jump. Now, I know this is kind of like complicated, but again, review this diagram that I showed here and you should be able to kind of follow it. Okay, well, let's see if it compiles. And it actually does. So let's kind of go over the code to make sure that we did everything, that we didn't leave any mistakes here. And it seems like, yeah, and let's go to the top. So we have the function, we have the prologue, set the stack, we got resolved base DLL base for NT.DLL. We got the names here, skip this section if we didn't resolve load DLL, called it. Then we have resolved, we resolved the string for the API. And let's see, we got the address for it. We actually restored stack and returned, ESP. We checked for failure, and the failure basically is this. And then we adjusted the stack, and we called NT unmapped view of section. So technically that should work. And let's go to release. And let's see in here. Let's see, do we have to adjust structured exception handling? And no, it actually compiled as well. Okay, so guys, at this point we have our shellcode completely done, and the shellcode again is will be injecting our DLL into the target process. So the only thing that we have left, we need to expose this function somewhere from our DLL, because right now it's just a function internally, so it doesn't really get exported. So let's do it right now. So first of all, let's copy it. And if you remember, a long time ago we created this Exports.def where we didn't add anything. And that's where we actually need to add our function and export it by ordinal only. This is what it means. This is the function name. Again, this is our assembly function. We export it by ordinal, which is 1, and no name means that it doesn't have any export name. So let's build it and let's see if it actually works. So let's rebuild it, and it doesn't. Oh, well, keep making the same mistake. I have to go back and prevent the 32-bit from building here. Let's do the same thing for debug build. Again, unfortunately, again, there's like 4 configurations here, and it's kind of like hard to keep track of all this stuff. Let's make sure that 64-bit actually builds, and it does. And let's do the same with release. Okay, well, now let's test something. So if we pull up our project and let's check x64 release and FAKE.DLL, let's see if it has any exports. And it doesn't. Now let's see why so. Okay, well, let's see if we actually specified it for let's see, for inclusion. Let's see library. Let me see all options. Okay. Okay, guys, stupid mistake. I had an old version of WinAPI search, so let's do it again. Okay, so now it shows that we have one export. It goes by ordinal, and that's what we needed. So that is one thing. And what we also need to do, we need to put this as our external parameter into our DLL main. And I'll explain why, just a second. Let's just do it right here. Extern C and void std call. And here you go. Now, when we build this module, if you remember, we set control flow guard. I think it was all options here, control flow guard enabled, and we actually set this special loader function, loader C file that would enable control flow guard and would provide all the like internal parameters. And back then I told you that we will need that to be able to inject our FAKE.DLL in certain processes which have mitigation policies that require control flow guard. Well, the way this control flow guard works, one of the options is that it is called Export Suppression. And anything that is not marked in this DLL as allowed export, in other words, you know, any of the functions that is not present in this module, it will be considered illegal. And when something calls one of those functions, well, it will crash the process. This is just kind of like a security basically thing that ensures that DLL injection and API injection doesn't go through. So some secure processes have this kind of thing. Well, the problem for us is that our UserModeNormalRoutine is not really marked as external function that can be called. Okay, so this will not pass export suppression restriction. So what we need to do, we actually need to call this function somewhere inside of our module, and not just call, but provide it as a callback. And the easiest way to do this, as I found it, is to create just an external exported function. So let me do it real quick. So let's do decl spec, and this is DLL export. And what we're doing is just providing a dummy export function from our module, and we will actually use it for something else. So let's say dummy export function, and let's say it should never be called. And what we do in here, we basically call, we use this as a callback for an internal APC setup. And what we do, we would call NT, one of the functions from NT.DLL. I think that is the name. Let me just try Q. It's one of the functions that are exported from, what am I doing? From NT.DLL. And let's see if I'm correct. So it's CWQ-APC thread. And what this does, this is kind of like an alternative for queuing APC from a user mode. And let's copy it and make sure I did it right. So it's undefined, so let me look up definition for it for you. It's basically very simple. Let's see, do we have any DLL types here? We do, and we do have some undocumented functions. So let me add it here. So basically what it does, it takes thread, it takes APC routine, context, and 2 arguments. Kind of the same thing as we did in kernel, except this is the user mode function. And what we need to do here, we don't really need to provide any parameters. We can just put like zeros everywhere, because again, this function will be never called. The only reason we call this is so that we can keep this UserModeNormalRoutine as marked for export, as not marked for export suppression in our control flow guard. Now, this is kind of like confusing, I understand, so please read on control flow guard and on export suppression. Let me just look it up real quick. CFG export suppression. And so one of these blog posts, I think Microsoft's one, actually explains it. And you should be able to figure out what this export suppression is. But again, in this case, we need to provide it somewhere for external, to be called externally inside our module, so that it can be called with the control flow guard enabled. Okay, let me see if I can just summarize it in a couple words. The following is needed to mark this function. Let's see, function as a valid call target when CFG is enabled, right, with the export suppression option on, otherwise invoking it for our APC will crash the target process. Okay, and because this thing is exported, it will never be called, well, unless someone is stupid enough to actually call it. And so we will this way we will provide this callback for the CFG. So let's rebuild it. And let's make sure that this F1 is actually included in the exports. So again, let's drag it into WinAPI search and search by it, and sure enough, we have it exported. Again, we don't really need it. It's just there for this control flow guard trick, so to speak. Okay, at this point, guys, I will stop this. So we're done with our APC callback. We coded it in assembly and provided a insurance that it passes control flow guard's export suppression. And now we can move on to the next task, which we will do next time. So thank you very much for watching, and I will see you then.